The last reaction of aromatic compounds that we want to discuss is the reduction of aromatic rings. So I've set up sort of three reactions here. So let's label them A, B, and C. If we look at reaction A, we're reacting styrene. This is a molecule called styrene. It has a vinyl group or an alkene as a substituent on benzene. Hydrogen and nickel at 100 atmospheres at 150 degrees. So this is pretty strong conditions, pretty forcing conditions, and we're actually going to be able to remove all of the double bonds here. If we react styrene with our standard alkene reduction process, hydrogen, palladium, 2 atmospheres at 25 degrees C, that's a pretty standard alkene reduction process. We're going to find that we can reduce the alkene substituent, but we don't reduce the aromatic ring. And again, that's because of the extra stability incurred by being aromatic. So we can reduce selectively just the alkene that's hanging off the ring, but we cannot reduce the alkenes in the ring using these milder reducing conditions. There's something more else that we can do with the ring, and that's actually quite interesting. If we look at this mixture of sodium metal, remember that sodium metal is metal, it's neutral, and it has a single electron, as we know that the element sodium has. Mixed with methanol in probably liquid ammonia. This is sort of the dissolving metal reduction reaction that we saw back in the alkyne section. We're going to use similar conditions here. And again, we're going to get radical reactions. We're going to use single barbed arrows. And so basically the sodium donates a single electron, and we split apart one of the electrons in our aromatic ring to make this radical anion. It turns out that electrons don't like to be next to each other, so chances are this anion undergoes some more, we call this resonance, to make this version. So I still have the anion on the top carbon, and you'll notice that I moved the radical down to the bottom carbon. So now my radical, which has high electron density, and my anion, which has higher electron density, are as far apart as they can be from each other. And this is their desired state for the brief period of time that we have this radical anion. The next step is to take a hydrogen from methanol using our standard proton transfer mechanism to protonate the anion, leaving us with this radical. Then another electron from sodium is donated right to the first, or the original radical. We have another anion, and I'm going to draw this back here because we're done. This anion, and again a standard proton transfer mechanism, produces the neutral species. And so you can see that we've reduced 2 of the carbons on the benzene. We still have 2 alkenes present, but we don't have an aromatic ring anymore. We have 2 isolated double bonds. This is pretty interesting. Now we've found a way to take benzene and turn it into 2 isolated double bonds that we could in turn do other reactions with, such as a Diels-Alder reaction. Let's look at how other substituents can affect this reaction. So what I want you to take home again before we move on to the next page, we will always form CH2s opposite each other in the ring, so at the 1 and the 4 positions. So that's going to be always what we form. And also remember that the intermediate is this radical anion. Okay, that's going to play a role in helping us to predict the regiochemistry if we have an unsymmetrical benzene ring. Okay, here we have a couple of unsymmetrical benzene rings. We have one ring with an electron withdrawing group, and we have one ring with an electron donating group. And so how do these substituents affect the outcome of the reaction? So how do you think an electron withdrawing group would treat that anion? Would we want the anion to form next to that electron withdrawing group or away from it. Let's look at a potential intermediate. We're going to use the same mechanism we used before, but now if you look at this intermediate, I now have some resonance stability for this newly formed anion. And that's going to be very helpful in stabilizing that particular setup. So the product in this case will be the reduced carbons, one of which is adjacent to the electron withdrawing group. So when we have an electron withdrawing group, we will form this setup where we have one of the reduced carbons adjacent to that electron withdrawing group. Let's look at the situation with an electron donating group. What if we put the anion in the same position? Remember that I said that the radical and the anion form at opposite ends of the ring so that they can get as far apart as possible from each other. But look at what's happening with my electron donating group and this anion that's forming on the carbon. We now have a bunch of lone pairs on the electron donating group and a newly formed lone pair right next door on this carbon. So this is a pretty poor situation. Not to mention that electron donating groups tend to be pushing electrons away from them into the ring here. So this carbon here is already pretty electron rich, and so adding more electrons to it is probably not the best situation. So I'm going to cross this off in red, and we're going to draw the other option, which is this option, where the electron donating group is not connected to that carbon that bears the anion. That's going to be the situation that happens in this case because of the bad interactions that I described in this first attempt. And so once we add some hydrogens and we add another electron, this is the product in this case. So you see that when we have an electron donating group on the ring, we're going to form the reduced carbons on carbons that are not next to the electron donating group. And that's different from when we had an electron withdrawing group. We formed the reduced carbons next to the electron withdrawing group. Notice again, the reduced carbons are at 1 and 4 position in the ring, so you're always going to form that pattern. It's just a matter of where does the substituent end up. So you need to decide whether it's electron withdrawing group, which might stabilize the anion, or is it an electron donating group, which would destabilize the anion, and thus we'd get a different regiochemical outcome in this Birch reduction.